All right, everyone, welcome back. This is lesson 7.2.2, Properties of Rhombi. That is just the plural of rhombus. And while this main question here is what is special about a rhombus, this is not our biggest focus today. Our biggest focus is really on upgrading our proof style and making sure we are justifying every bubble that we have. So we have a rhombus over here. It looks like a tilted square. A rhombus is defined as having 4 congruent sides. So we can go ahead and notate this with tick marks. All of them are congruent, not just opposite sides. So that's very nice for us. We have a teammate that believes that the sides of the rhombus might have other special properties. Okay, another special property that rhombi actually have is that the opposite sides are parallel to each other. And reminder, the way we notate parallelism is with angles. So PQ and SR are parallel to each other. And then QR and PS are parallel to each other. So I'm going to use 2 arrows there to show that not all of these are parallel. So the next instruction is to add diagonal PR. So going from P to R, this is a diagonal here. And it's asking us to create a flowchart proof, which we are masters at this point, with reasons though. That's the new part for us, justifying every bubble, showing that these triangles are congruent. So reminder, for congruence, we need one of those congruence theorems. So SA, side, 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 angle, angle, side, or hypotenuse, leg. So when it's asking us to prove that they're congruent, we are looking for one of these 5 things. Okay? Well, we've already looked at, in terms of triangle 1 and 2, we have one triangle here, another triangle here. We have equal sides, and 2 of them in fact. So side, side. And then we know from reflexive property that that is a shared side right there. So we are going to use side, side, side congruence to prove that those 2 triangles are congruent. So let's start off with this first side, PS, okay? PS on one triangle, side PS is congruent to side RQ. And this one, because they're all congruent, it doesn't have to be RQ. You could have said that PS is congruent to PQ. Okay, and the reason for this is from the definition of a rhombus. That is a good enough reason. Okay, they told us that in a rhombus, all the sides are congruent. So our reasoning for saying that is just definition of a rhombus. Okay, now we have the other sides. Side PQ is congruent to side SR. And again, we know this because that is from the definition of a rhombus. Nice, easy reasoning there. Finally, though, our third side that we're talking about is this shared side, which again we call reflexive property. So we can say side PR is congruent to side PR. And that one is not because of the definition of a rhombus. That we used the reflexive property for. And with all this, that gives me side, side, side congruency. So that is enough to say that triangle PSR is congruent to triangle, let me make sure I do this in the right order here, RQP. Okay, and this is because of side, side, side congruence. So the only thing that was different here that we're not used to is using some reasoning. Okay, now we know the triangles are congruent. We've proved it. Can we say that our teammate was correct? Are these opposite sides parallel? Well, we can look at the angles here. If these triangles are congruent, it means their angles are equal too. So we've got equal angles, alternate interior angles, which we know if alternate interior angles are congruent, then the sides are parallel. So yes, we can say that our teammate was correct because we have alternate interior angles that are congruent, which means that the opposite sides are parallel. That's the symbol for parallel. All right, this next question, we're gonna edit a little bit. It says your teammate believes that the diagonals of a rhombus are perpendicular. We are going to change this to bisecting each other. The diagonals bisect each other. And we are supposed to prove this using a flowchart. Now, reminder, to bisect simply means to cut in half. Okay? So we're basically trying to prove that if we had two diagonals in this rhombus, diagonal 1 and 2, that they basically cut each other in half. So we're trying to prove that this chunk right here and this chunk are equal, and this chunk and this chunk are equal. Now, one thing I'm going to add in is I want to call this point where the two diagonals intersect, I'm going to give that a letter so that when I'm proving things, I'm able to use letters to talk about, for instance, this segment. This segment is RT. Okay, you are allowed to do this. So let's start with what we know about a rhombus. We know all the sides are congruent. So different color here, I'm going to mark. I've already used some markings, although that's what I'm trying to prove. So I'm gonna go ahead and get rid of those markings here. But we know that all the sides of a rhombus are congruent. So I can go ahead and say something about those. Again, I am looking to prove that these triangles are congruent. Okay, so I am wanting to look for one of these 5 congruent statements. So let's start with the fact that all the sides are congruent. I'm going to start with PQ is congruent to SR. So side PQ is congruent to side SR. And the reason I know this is from the definition of a rhombus. Sides are congruent. Okay? Now, because I also know that sides of a rhombus are parallel, I actually have a set, actually 2 sets of alternate interior angles because opposite sides are parallel. So I have one set here in green and another set here in dirty water brown of alternate interior angles. I'm allowed to say those are equal. So the green ones, actually, I want to focus on these 2 triangles here. So I'm going to put that dirty brown one somewhere else. I'm going to talk about how this pair of alternate interior angles are equal so that I now have a triangle with angle side angle congruency and another triangle with angle side angle congruency. So my first set of alternate interior angles that I'm saying are congruent is angle PQT. That angle is congruent to angle RST. So I'll show you where that is. PQT, this is the brown one, is equal to RST. I'm doing this set of angles right here. Oops. RST. And I'm allowed to say this because they are alternate interior angles. And then for my second set of alternate interior angles here in green, I'm going to do the same thing. Angle QPT is congruent to angle SRT. And again, that is because they are alternate interior angles. And now we have two triangles with SAS. Side, angle, side, congruency. Those two triangles that were highlighted in blue, I just want to highlight the fact that we have, oh, I'm so sorry, this is not SAS, this is ASA. We've got angle, side, angle, congruency. So I can say, because of these things, triangle PTQ is congruent to triangle RTS, and that is due to angle side angle congruency. Now, you're going to ask yourself, I thought we were trying to prove that the diagonals bisect each other. Okay, well, we know from CPCTC, congruent parts, corresponding parts of congruent triangles are congruent. So now that I've said that the triangles themselves are congruent, their parts are congruent, their corresponding parts. So I could say that side PT is congruent to side TR. And that is due to CPCTC. Let me show you what sides I'm talking about here. PT, this chunk, is congruent to TR. Those are corresponding parts of the triangles. And if I did that same thing for the other diagonal, saying that the two parts that make up the diagonal are congruent, QT and ST, and again due to CPCTC. Well, what I basically said, and I'm sorry, I'm going to erase this all to show you what I mean here. What that basically did is my two diagonals here, because I said my triangles are congruent, the corresponding parts, so this line and this line are congruent, and this line and this line are congruent. They are bisected at the midpoint, okay? These diagonals have been bisected by each other because these parts are congruent. They've been chopped in half. Now, we had to do a lot of work to get here, okay? That's what CPCTC is. You often have to prove something where in order to even get there, you have to prove that the triangles themselves are congruent first, okay? All right, moving on, our teammate is attempting to prove that opposite angles in a quadrilateral are congruent. So we're trying to prove that C and A are congruent to each other. Now this one, they've given us a little starting point. Okay, they're telling us this is a parallelogram that's given to us. Based off what we know about a parallelogram, we know that opposite sides are parallel. So side TU is parallel to WV, which we know because of the definition of a parallelogram. And we know that about the other opposite side. So that's something we could fill in. We could say that side TW is congruent to side VU. And I'm sorry, not congruent, parallel. Because of the definition of a parallelogram. We know this about a parallelogram. We can use this information. So from that, apparently we can say, and this is poorly written, this should say angle B is equal to angle C. Okay? Why is that? Well, let's look at B and C. B and C are in corresponding locations. These are corresponding angles. So the reasoning for this, that we could say angle B and angle C are congruent, is because they are corresponding angles. apparently the next reason, or the next thing we have reasoning for, is if lines are cut by a transversal or parallel, then the alternate interior angles are congruent. So it must want us to talk about a pair of alternate interior angles here. Well, A and B are alternate interior angles because we have our parallel lines and the transversal. So let's say that A and B are congruent. Angle A is congruent to angle B. And the reasoning was given for us. All right, here is where we have something new called the substitution property. The substitution property here can be used like this. We said angle B is congruent to angle C, right? But we also said that angle B was congruent to angle A. So if A and C are both equal to B, then it's fair to say that A and C are equal. And this is what we call the substitution property. So we can say that angle A is congruent to angle C because of the substitution property. And that's what we were trying to prove. We were trying to prove that opposite angles in a parallelogram are congruent. So that's something we can fill in our shape sheet that we will do later. But basically, for a quadrilateral, we learned that opposite angles are congruent. And we did learn more, which I will fill in on the shape sheet in a different video.